Before we start, let's review the extreme value theorem. Okay, for the extreme value theorem, if a function is continuous on a closed interval, then you're guaranteed a max and a min somewhere on that interval. Now, the maximum could occur at the endpoints. That's very important for what we're doing today with the closed interval test. Or it could happen at a critical number that's inside your interval. If you'll notice this open interval, there is no maximum value because there's no highest point, and there's no minimum value because there's no lowest point. So you're not guaranteed to have an absolute max or an absolute min if you're continuous on an open interval. Also, if your function is not continuous, it is possible to have an absolute minimum or an absolute maximum, but there's no guarantee of that. You'll notice here our function goes up forever because we have that asymptote. So if your function is not continuous, there is no guarantee of an absolute max or absolute min. So here we go, we're doing the closed interval test. If you're doing the closed interval test, you don't need to do all that work that you did when you filled out your chart for the first derivative test. So that's why I'm crossing that out at the bottom. Okay, for the closed interval test, you're still going to find your critical numbers. Where is your derivative equal to 0? And where is your derivative undefined? Those will be your critical numbers. Now, you're not always going to use every single one of those critical numbers. For example, if we're going from 0 to 6, if that's our closed interval, then we will only use the critical numbers that land inside that interval. So if our function actually continues on, and we get another critical number over here on the left, we're not going to use that critical number. We're going to throw it away because all we care about is our closed interval. Now, when we did the first derivative test, one thing we did not care about were endpoints. Our closed interval is going to have endpoints. When we do the closed interval test, that's the extra thing we have to check. We've got to check the endpoints. So we're going to check the endpoints, and we're going to check our critical numbers that land inside of our interval. Now, the way you do the closed interval test is once you've identified the two endpoints and you've identified all your critical numbers that land inside that interval, now you just plug them into the function and see which one's the biggest. The biggest will be the max, and see which one is the smallest. The smallest will be the min. So we're using the closed interval test to identify an absolute max and an absolute min, not necessarily a relative minimum or relative maximum. Okay, let's do an example. We have our function. It's a quartic function. The degree is 4. And we're going to evaluate it on the interval from 0 to 6. So we already know our endpoints. Our endpoints are going to be 0 and 6. So here's our final answer right here. We plug in a 0 and a 6 because those are the endpoints. The other thing that we have to check is the critical numbers. You'll notice after doing the derivative and setting it equal to 0, we're going to get 3 critical numbers, but one of them, which was -3, does not land inside of our interval. So you see I crossed it out. The only numbers that land inside of our interval are x equals 2 and x equals 5. So again, here's our final answer. We just take the two endpoints, x equals 0 and x equals 6, and we take our two critical numbers that land inside of our interval, x equals 2 and x equals 5. You plug them into the original function and just see how big they are. The biggest one is the absolute max, and the smallest one is the absolute minimum. I want you to notice that an absolute maximum or minimum can either happen at an endpoint, like it did for us in this example, or it could also happen somewhere in the middle where we have a critical number. So we're not filling out our chart for the first derivative test. We just find our critical numbers, plug them in, and see how big the function is at that spot. And we also plug in the two endpoints and see how big the function is at that spot. Then we just look at all the answers. The biggest one is the absolute max. The smallest one is the absolute min. And that's it. Okay, let's go ahead and do a trig one. Here our function is going to be sine of 2x. We have a picture of sine of 2x over here. And we're going from x equals 0 to x equals 5. Visually, you can see that there's one absolute maximum here, there's one absolute maximum here, and we have an absolute minimum in the middle right there. So we can see what the answers are going to be before we actually do the problem. I also want to point out that there are two absolute maximum values. If it was a horizontal line, every point would be an absolute max and an absolute min, but that's just a weird example. Okay, let's go ahead and do this problem. Remember, we're going to use our endpoints, so we'll plug in 0 and we'll plug in 5. We're going to plug them into our original function, and then we're just going to see how big the value is, see how small the value is. Okay, we also are going to have to find our critical numbers and check the value of our function at those critical number values as well. Of course, this is a trig function. It's going to have an infinite number of solutions. So we just want to find the ones that land in our interval, which is from x equals 0 to x equals 5. The derivative of sine is going to be a cosine, but it's not just an x, it's a 2x. So we have to do the chain rule. We have to do the derivative of 2x, and that's where we're getting this extra 2 from on the outside. Okay, we know what cosine looks like. It's never going to be undefined. So our derivative will never be undefined, but we also know that cosine can equal 0. So we want to find out where our derivative is equal to 0, and that will give us our critical numbers. So we start by dividing both sides by 2. Then we're going to let 2x equal theta. We're going to try to figure out where does cosine of theta equal 0. We know what cosine looks like. We have the graph over here on the right side. It's going to equal 0 at pi over 2, but also 3 pi over 2. Now we know that cosine continues forever in each direction. So if we keep adding 2 pi to those answers, we're going to get all of the other answers that we want. Okay, before I start plugging in values of k, I want to remember that I let 2x equal theta, and I'm trying to solve for x, not really theta. So I want to trade the theta for 2x, and then I'll be able to plug in different values of k. So here we go, we trade theta for 2x. You'll notice we still have to divide everything by 2. That gives us this answer right here. Same thing on the other side, we trade theta for 2x, and we get this for our final answer. Now we can start plugging in different integer values for the k. I listed some of them at the bottom. Same thing over here. Plug in different integer values for the k. I'm listing some of those answers at the bottom. Now the reason why I'm throwing these out is because they don't land between 0 and 5. We need all the critical numbers that land between 0 and 5. And if you type those numbers into a calculator, you'll see that they are either more than 5 or less than 0. So only these values in green are going to be allowed as critical numbers that we're going to use for our closed interval test. Okay, so now we're at the end of our problem. We found our critical numbers. And we're also going to use our endpoints. We plug them into our original function and just see how big they are. The biggest one is going to be your max. So we have 2 absolute maximum values, and we have 1 absolute minimum value. In this case, the endpoints didn't give us anything. You can look at the graph of our original function over here on the left side, and you can see our answer. Pi over 4 was an absolute max, and so was 5 pi over 4. And the absolute minimum occurred at 3 pi fourths. Okay, let's look at how we can solve this equation with a graphing calculator. And we should expect to get these answers. Let's take a look. Okay, the solve is going to be in F2. We're going to do comma x. And don't forget the right parentheses. Then we'll go back inside, type in the equation. Our equation is cosine of 2x equals 0. If we push enter, we're going to get a rule to find all the solutions. We have an infinite number of solutions. We just want the ones between 0 and 5, so we can evaluate it on this interval from 0 to 5. If you have the new operating system, it'll work. You can just push enter and it'll work. The online simulator uses the old operating system, so we're going to have to write it a little bit differently. We're going to have to say when x is greater than or equal to 0, and you can get the and from the catalog. Just go to A, it's the second one, and then x is less than or equal to 5. If we push enter, it will give us our 3 answers. You get 5 pi fourths, 3 pi fourths, and pi fourths. You can't see pi fourths, so you have to go up, push right a little bit, and there it is, pi fourths. So that's how you can use your graphing calculator to solve the equation for you. Okay, this last one is just a review question. Remember, we're doing the derivative of a function. to a power that's also a function. How would you do that? I want to point out that we're doing d dx, but this is not an x, it's an f, and this is not an x, it's a g. I also want to remind you that the derivative of a number to the x is number to the x times ln of that number. And the derivative of x to a number, the number comes down and the new power is 1 less. This is neither of those things because f is not a constant and g is not a constant. So here we go. I'm going to write this as y. I'm doing it right here. But I want the derivative of this. So my final answer is going to be the derivative of y. Okay, let's do some pre-calculus stuff. We'll do ln of both sides. And that's going to allow me to bring this power down in the front, so I get the g in the front. Now I can do the derivative. Remember, the derivative for ln of x is just 1 over x. So the derivative for ln of y is just going to be 1 over y, but it's the wrong letter, so we're going to have to put y prime. What do I mean by it's the wrong letter? Well, we're doing d dx, but this is not an x, it's a y. So that's the reason we need this y prime piece. Now on the right side, we have a product rule where the first is the g and the second is the ln of f. Remember the product rule? You're going to get the first times the derivative of the second plus the second times the derivative of the first. Again, these two things can be switched. It doesn't matter which one goes first. Remember in the beginning, I said that this was y, so our final answer is going to be the derivative of y, and so our final answer is going to be y prime. But we see a y prime sitting right here, so that y prime is going to be our final answer. We just have to do a little bit of simplifying. We don't have to really do anything with g prime. The derivative of g is just g prime. There's nothing to do there. We haven't done the derivative of ln of f yet. Remember, if it was d dx of ln of x, that's just 1 over x. We have d dx of ln of f. It's the wrong letter, so you'll get 1 over f, but then we're going to get f prime. So that goes right here. The derivative of ln of f is going to be 1 over f and then f prime. Again, we're trying to solve for y prime, so we got to get rid of this 1 over y. We can get rid of it if we multiply both sides by y over 1. On the right side, you have to put these parentheses because we're multiplying everything by y over 1. You can see on the left side, this y on top cancels with this y on the bottom, and you just get y prime. A lot of people stop here and they think they're done. But remember, our original problem, we were trying to find the derivative of f to the power of g. So it doesn't make any sense to have y's in our answer. So don't forget to trade our y for what it was in the beginning. It was f to the power of g. So we'll do that substitution right here, and then we're done. Final answer is in that blue box right there.